Now we will take up a problem, a beam problem, analysis of beams. So, the same example, whatever we worked in slope deflection method, so the same example we will work in moment distribution method also. The three problems, whatever you did, analysis only for the member loads, that is this 50 kilonewton per meter, 80 kilonewtons on this member, which is 4 meter, here it is 6 meters, along with a overhang load of 10 kilonewtons at 2 meters, and this value of flexural rigidity being EI, here it is 2 EI. So this is A joint, B joint, C, D. So this beam we analyze. Here I have given the mid support settles down by 120 EI. That also I have taken. There is a settlement load also is included. A settlement load, member loading, as well as overhang load. All this, instead of considering three problems separately, I have considered only one problem. I have included all types of loads. So you can work independently, treating each as separate example and verify your total final answer. Now this problem will work by moment distribution method, MD method. So the first step, so as we explained in slope deflection method, the first step remains same. That is, in the first step you have to identify what are the unknowns to be determined during analysis. The unknowns to be determined during analysis are member end forces. Member end forces will be shear as well as moment. Out of that, we select only the moments at the ends as the unknowns. So first step, you say selecting moments at ends of members as unknown forces to be determined during analysis. So you can show what all the forces to be determined. So these are the things. So the moment at the ends. So that is MAB, then here MBA, here MBC and MCB. All I have taken clockwise because positive direction only I have taken. So we have to determine the moments at the ends of members as the unknown here also. If you treat this as a member, normally we don't treat this as member. If you treat that member also as a member, then this is the member and moment, that is MCD, CBA. So this moment is known. This MCD is nothing but minus 20 because this moment will be acting resisting like this, applied will be like this, resisting will be like this. Since we are taking all moments in the positive direction, diametrically, so this is already known. Only unknowns are 4. So these are unknown forces to be determined during analysis. When unknown displacements to be determined during analysis, that also you mark it as you did in slope deflection method. The unknown displacements, here it is fixed, no displacement is possible, so there is unknown displacements are 0. Here we assume axially rigid, horizontal displacement is not there, vertical displacement because of this prop, vertical displacement is also not there, only a rotation which is possible, theta b Same thing here, only rotation, theta c. So these are the only two possible displacement with reference to the global coordinate system x, y, z. With reference to these global coordinate system, the forces and displacements to be determined during analysis are this. So there will be three types of forces because it is plane structure. Out of these, this translation is not at all there. This translation is not at all there because prop is there. It's a non-sway, only moments. Out of the moment here, it is not there, only at these 2 points. This is your unknown displacement or kinematic indeterminacy. Kinematic indeterminacy to be determined. So this is your first step. Why we have to do this step means, so to identify whether given frame is sway or non-sway type, we have to do this. So why we are doing this means, this is what we are analyzing. Even slope deflection method also, this is what we are doing. So this also to be written, static and kinematic indeterminacy. So this is your kinematic indeterminacy. This is the very first step wherein we identify what we have to determine during our analysis. Next, second step is stiffness and distribution factor. So this is the one. There in slope deflection method, second step is writing slope deflection equation. I told you already that slope deflection equation, formation of equation and solution, all those things will be eliminated and it will be done by this determination of stiffness and a moment distribution table in a simple way. So this is your second step here. First step, same as slope deflection equation. Second is stiffness and distribution factor. Since it is mainly distribution factor, so this distribution factor will come into picture only at the joints where more than one member is there. There only we have to determine the distribution factor. Otherwise there is no question of any distribution if one member is there. If one member is there, if that end is fixed, you take distribution factor as 0. If one member is there, only one member, and if that end is simply supported, hinge or roller, you take distribution factor as 1. Now remembering that, only you have to determine the distribution factor. That you write joint. So only at the continuous joints you are determining. Continuous joints is only B. C is simply supported joint because this overhang we don't consider as a member. You should neglect that. This is just a simple joint, simply supported joint. Distribution factor is 1. Here it is 0. Only here we have to evaluate. So joint B only, then members meeting at joint B. There are 2 members meeting at the joint B. One is BA member, another BC. These are the 2 members. Then write stiffness or relative stiffness. I will write relative stiffness K of member. Member BA. Member BA. It is fixed at one end, continuous at other end. Relative stiffness is I by L. What is I of the member? It is I itself. L is 6 meters. So it is I by 6 relative stiffness. Then coming to BC. BC member. One end is simply supported, other continuous. If one end is simply supported or hinge or roller, then relative stiffness will be 3/4 I by L I told. So that is 3/4 of I. I value of this member is 2I, L is 8. So it is 3/4 of 2I by 8. That will be 3I by 16. Then find total stiffness at the joint. That's total stiffness is required because for calculating distribution factor. K of the member divided by sigma K. That sigma K I will determine. Sigma K is I by 6 plus 3I by 16. LCM is 48 is the LCM. So this will be 8I, this will be 9I, 8 plus 9, it is 17I. This is the total stiffness. The distribution factor, that is K by sigma K. Distribution factor for the members. So that is K by sigma K. That is I by 6 by 17, I by 48, that is 8 by 17. Here it is 3 by 16, 17 I by 48, that is 9 by 17. Remember, always sum of the distribution factor at any joint will be 1. This is an important property. After calculating this, you can check your research whether distribution factor you have calculated correctly or not. You can check here at the end. Add the distribution factors at each joint, that sum should be 1. Make sure that. And of course, distribution factor for A, you can take it as 0. Distribution factor for C, you can take it as 1, because it is simply supported in that
C.
So this is second step. Then third step, you have to do fixed end moments. Fixed end moments. Whatever I just explained. The fixed end moments at the ends of
distribution factor at joint C is 1, right, sir?
C. This is
C.
C. Okay. So fixed end moments you have to find out for all the members. You take member AB because we assume all loads to be acting only at the joint. So here loads are acting at the members. So you have to find equivalent value at the joint with its sign reversed. Automatically that sign will reverse because I told you while determining fixed end moment, applied moment is like this. This is resisting. I reverse that, it is built in. In matrix method, there is a set procedure, same thing. It's absolutely, there is nothing. So fixed end moment, we take MAB bar, that is for AB, due to UDL, that is WL squared by 12, that is 50 into 6 squared by 12, that is 150, so that is minus 150. So if you want, we can show that. AB due to this load, this moment is 150, here it is 150, this is minus 150. This is due to load. Then due to settlement. Settlement, this member undergoes a settlement like this in the clockwise direction, so it is anti-clock moment. This will be minus because this settlement will be like this. This, due to this, the moment developed at AB, it is anti-clockwise, so that is minus. That moment will be 6 EI delta by L square. That is 6 into EI is EI itself, delta is 120 by EI, L square is 6 square. This, if you work out, it will be 20. So this will be 20 due to settlement of support. There is no overhang for the member maybe, you leave it. So this is just minus 170. Then MPA bar, due to given loading, it is plus 150
minus,
and this is minus 20. So it will be 130. Then MBC if you take ends BC, so load is 84 meters, 4 meters, this will be WL by 8, that is 8 into 8 by 8, it will be 80. 80 in the anti-clockwise direction, so it is minus 80. Then due to settlement of support, it is like this. This is anti-clockwise, so it is positive. Its value will be 6 into EI. EI is 2 EI, delta is 120 by EI, L squared is 8 squared, that is 64. So this, if you simplify, I think it is 22.5. So that is positive. So it is plus 22.5. So this comes to 0.5.
Minus 57.5.
57.5.
Minus 57.5.
Minus. Then MCB bar, it will be plus 80 plus 22.5, it will be 100.5. These are the
102.5.
fixed element. Then due to overhang, MCD is minus 20. That already I have written here. Yes. So these are the fixed element. This is third step. Clear?
That's a 120.5, sir. MCB.
Huh?
MCB.
Which one?
80 plus 22.5. MCB bar.
MCB.
MCD bar.
Yes. No, sir. That one. 100.5. That is 120.
MCD bar.
No, sir. That is right, sir.
Yeah,
MCD bar
okay.
equals 80 plus.
MCD.
Yes, sir. 80.
BC MCD.
MCB 80 plus 22.5. That is 102.5.
102.
2.5.
100.
Yes, sir.
It is actually
102.5.
It's okay. So this is third step. So first step, identifying the unknowns to be determined. Second step, stiffness and distribution factor, whatever I have told earlier, that is by definitions. Third step, fixed end moment. Now we have to do moment distribution. So moment distribution we call it as non-sway moment distribution, right? Because it is non-sway. Then if it is sway frame, we have to do one more moment distribution, that is for sway moment. So then we have to add it. Sway moment problem is it is a little bit more involved because 2 times we have to do the moment distribution table. Otherwise, if it is non-sway, very, very simple. Now you watch it. So the next fourth step, moment distribution, that is fourth step, moment distribution. That is called, now what we are doing now is non-sway analysis. Non-sway moment distribution. If it is sway, one more time we have to do moment distribution, that is for sway analysis. Then we have to do non-sway and sway together at our end. Otherwise it is only non-sway. That's all the work. The moment you do this distribution, you will get these unknown moments, MAB, MB and all. That's all the solution for the problem. So this is the only table which you have to remember. These definitions, and that is fixed time moment known. This also you know there is no much about it, only this is the extra thing which has been told to you now, you have to remember, and this moment distribution table. This moment distribution table is nothing but a table which represents all the data, whatever I have worked out in the form of a table. That's all. Whatever I did here now, that is distribution factor, joint, member, fixed end moment, all those things I will write it in the form of a table. So first I will write joint, write joint. Next, you write member. This I will fill it up. First, joint A. many members are there at the joint A?
One.
Only one member, that is AB. You write, that's all, over. Then joint B, there are two members, BA left side, BC right side, because it is a continuous joint. BA, BC. Then joint C. CB is the only actual member. CD is just a overhang, it is not a member, but I will just take it. Can take it in overhang problem in moment distribution like this, because the fixed end moment I have taken to write that I am taking this at the joint. D you don't take it because D we don't take it as a joint at all, regular joint. Then you write stiffness. Not stiffness, distribution factor, straight away. I don't write stiffness, I write straight away distribution factor. Distribution factor at A, for AB, it is fixed and I told you distribution factor will be 0. I wrote it earlier. Distribution factor for a member where only one member is there, it will be 1 because there is no question of any distribution there. For member C, wherein only member, one regular member CB is there, it is hinged or simply supported, distribution factor is 1. For BABC, you have determined here. For BA, it is 8 by 17. For BC, it is 9 by 17. I have just transferred all the things. Stiffness, distribution factor, joint, member, all those things I have transferred. Now, fixed end moment. I write it. From here onwards, the moment distribution start. All these are all basic things, whatever you have determined, no problem at all. Fixed end moment, I will write it. So MAB, it is minus 170 for AB. And BA, it is 130. I'll write it. BC, I'll write it is minus 57.5. CB, it is 102.5. CD, it is minus 20. I will transfer all that, whatever I have determined here. Now I can simply have it down. Now I can just simply concentrate my work, analysis work, only on this table. There are only preliminary things which I explained earlier. Stiffness, carryover factor and all. There are preliminary ideas, including fixed end moment, due to settlement, load, whatever it is, overhang, whatever it is. From here onwards, distribution comes. That is, first we apply equilibrium condition. In slope deflection method, instead of writing slope deflection equation, I wrote this table. Next, I have to apply equilibrium condition. I will go on applying equilibrium condition, joint by joint. Joint A, right? Do you have equilibrium condition? As in slope deflection method, there also you are not having any condition because the joint A, it is fixed. Whatever we assume, all joints to be fixed. We got this moment, joint A is fixed itself, we have not committed any error. We have not committed any error, so there is nothing. This is called balance. So that equilibrium condition, whatever we are doing, that is balance. By assuming all joints to be fixed, we assume all joints to be fixed to start with. From that we got the moment. But in the actual problem, all joints are not fixed, only some are fixed, some are continuous, some are simply supported like this. So we have to apply equilibrium condition, satisfy that. So we have to balance that. So whatever error we have committed, that to be balanced. So the fixed end moment is the one, whatever we got by assuming all joints to be fixed. That is an error we have committed. That to be balanced by applying equilibrium condition. So automatically equilibrium condition has come into picture here. And formation of equation, solution will not come automatically. All those things are gone in this table calculation. Here joint A, no error committed, no balance. Here joint B. Joint B is not fixed. So by assuming fixed, you got this moment. So apply equilibrium condition, remove that error. So what is that equilibrium condition? MBA plus MBC, moment at the ends of members meeting at that joint has to be 0. That's what equilibrium condition you have. And joint B, MBA plus MBC has to be 0. Here it is not 0. What is the value here you got? That is
72.5.
70?
2.5.
72.5 plus 72.5 is the moment. What should be the balance moment?
Minus 72.5.
Minus 72.5. Because this MBA plus MBC has to be 0. This you have to clearly bear it in mind, applying equilibrium condition and do that balance for this fixed end moment to start with. So this 72.5, whatever the moment which is the error committed by assuming is to be fixed, that should be balanced. Balance moment will be minus 72.5. That will be at the joint B. It will be shared by the members. The balance moment will be shared by the members in proportion to distribution factor. This BA will take minus 72.5 into 8 by 17. This BC will take minus 72.5 into 9 by 17. So let us write that value. Straight away I have value here, I will write that. So here 1 minus 72.5 into 8 by 17, it will be minus 34.1. You also have this particular table with you already, it has been circulated. Similarly, minus 72.5 into 9 by 17, it is minus 38.4. So now you see this sum is 0, complete. This is plus 72.5, this is minus 72.5, it is 0. So you have achieved that equations of equilibrium. Next, go to the next joint C. So at this joint C, MCB plus MCD has to be 0 because CD is also coming because of overhang. Otherwise, overhang is not there means it is just MCB is 0. Right? Now MCB plus MCD 0. Now that is 102.5 minus 20,
82.5.
82.5 plus, right? But that has to be 0. So balance moment will be minus 82.5 and that to be taken by only CB member minus 82.5 into 1. Distribution factor is 1. So it is minus
82.5.
Now you see this MCB plus MCD, it is plus 82.5,
0.
minus 82.5, 0. That equilibrium condition is satisfied. So this is what is known as moment distribution, satisfying equilibrium condition, nothing other than that. So this we go on repeating until these balance moments becomes very, very small. It's a trial and error method. As you commit some error, assume all joint to be fixed. If it is not fixed, some are fixed, apply conditions of equilibrium, remove that error. Because while removing that error, you are making other ends of the members strain, carryover factor will be there. That is next subsequent thing. That you go on repeating this balance, carryover, until that balance becomes fully 0 or negligibly small. When compared to this initial value, see here it is 130, here if it is coming 1, you can stop your work, add all the moment, that will be work, MAB, MBA, MBC and all. That's all the basic principle of moment distribution. Nothing other than. That's as simple as that. So this, okay, so this we call it as cycle 1. First cycle of moment distribution, which we do only with respect to error, fixed moment. Now you watch. Here it is carry over. Because now you have removed those errors. But while removing the error, you are putting a moment at one end of the member. Because this minus 34.1, earlier it was 130, now it is minus 34.1, it is coming here for BA. It is coming for BA at the end B. Mind it is coming for BA at the end B. It will have an effect at the other end A, provided if that other end A is fixed or continuous. Because the carryover can be done only for fixed or continuous. If it is hitched, no carryover. So here AB to BA, no carryover. No balance moment, no carryover. Whereas from BA, which has come from B joint B, it will go to joint AB. Half this value, I told you carryover factor, right? Half that value. So minus 34.1 divided by 2, it is 17.1. Half that value. You can round it up to nearest digit, it doesn't matter. So this is over. Next, this balance moment has come for the member PC from joint B. It will have an effect at other end CB. Half this value provided if other end is fixed or continuous. So from BC to CB, how is that CB end? CB end is not continuous, not fixed. It is simply supported. That is why here you should not do any carryover. I am writing underline because even though overhang is there, that's not a member, it is not continuous joint, it is simply supported only. No, from CB to BC, CB to BC, it can come because BC is continuous. So CB to BC, it can come half this value, it is
minus 41.2.
41.3 and right. Then balance. One more balance. Because this carryover has come, whatever you have balanced here, satisfied equilibrium condition, that's gone now because of this carryover. Again, you have to do balance. So, this is next cycle, cycle 2. So, balance similar to this. Here, no balance. Here, this plus this.
41.3.
MPA plus MPC should be 0. It is minus 41.3. This you don't take. That's over. That is balanced fully. And because of this carryover, we are doing balance. Here it is, balance is plus 41.3. Then it will be 0. That plus 41.3 will be distributed in this proportion. So that will be, here it is plus 31.4, here it is plus 21.9. So now this is 0. Here MCB, MCD, 0. So no balance. Okay? Then we can do one more carryover. So this process, you will go on continuing until balance moments becomes very, very small. So next carryover from AB to BA, it is 0. From here to here now, it is 6.7. Half this value, BC to CB, it cannot go because that CB is simply supported. CB to
0.
BC, no balance, so nothing. Here, nothing. So no balance,
0.
nil. Here also nil. Here also balance moments, they are all 0. So you can stop. Automatically work is stopped. Otherwise, if it is continued, then when these balance moments become small, you can stop it. This is your cycle 3. After 3 cycles, the moment distribution work, it is over. So you say final moment. Whatever that MAB, MBC, MCD, those what you have to determine, that you get. You add all these fixed time moment, these are all due to the rotation, you will get minus 177.4, here 115.3, here minus 115.3, here 20, here minus
20.
Make sure MCD plus MCD is 0, MBA plus MBC is 0 automatically. So you have determined. We can plot last bending moment diagram. Last final step, we can plot the bending moment diagram. You can say the work is over. So you write arcs here at the ends of each member. Then indicate the arrow depending upon the sign. This is MAB. MAB is minus. Minus means anti-clockwise. So this is 177.4. MBA is 115.3 clockwise. This is 115.3 MBC. It is anti-clockwise minus 115.3. MCD is plus 20. This is minus 20. That's all. Now you superpose free moment diagram and fixed moment diagram. You will get the actual net bending moment diagram. So here by plotting, we have to plot it on the tension side. This is 177.4. Then here it is 115.3. And here again, same 115.3. This is 20. This side also 20. So you can join this. This is fixed moment diagram, whatever we got. On this superpose free moment diagram, whatever free moment diagram is there, so then you get the net moment diagram minus, or this is plus, minus. This is your net BM. So with this, I have completed non-sphere analysis of beams.